60,000 wafers a month stacked against 700,000, and the 700,000 are already shipping the generation after the 60,000 are aimed at. China's largest domestic memory maker raised roughly $4 billion to reach that 60,000 figure, and the export controls written to freeze the count are the same controls that pulled the investment toward it. This script takes two readings of a single metric, monthly high-bandwidth memory wafer starts, measures what moved between them, and reports the distance the funding headline does not carry. Near zero, that is the first reading, dated 2021 through 2022, when domestic high-bandwidth memory production inside China existed in no measurable commercial form. The largest domestic dynamic random access memory producer was still in early-stage output, and no Chinese supplier held meaningful capacity in stacked memory architecture. The instrument recorded a blank. Near zero, then. That is the baseline the $4 billion raise was built against. 60,000 wafers per month. That is the current stated allocation at CXMT, earmarked specifically for high-bandwidth memory at the third-generation specification, out of a total dynamic random access memory base that industry analysts estimate is approaching 300,000 wafers per month. The allocation figure comes from the capital raise and capacity announcement period spanning 2024 into 2025. It is reported across multiple industry outlets and analyst notes. It is not an audited production figure. That distinction matters, and the script will return to it. But the shift from near zero to 60,000 over roughly 3 years is real, and it is large. Nothing like it existed in the domestic count before the restriction regime that was designed to prevent it. Near zero, 60,000, near zero. That delta has a mechanism, and the mechanism is unusual. The policy meant to hold the number low created the only investment logic that could move it this fast. Before export controls removed the option of purchasing advanced memory capacity from outside China, no domestic political or financial rationale existed to direct sovereign-linked capital towards stacked memory architecture at this scale. The restriction converted a purchasing option into a manufacturing mandate. Capital followed the mandate. Cleanroom expansion, wafer handling equipment, process engineering. The roughly $4 billion funded inputs that the market alone would not have prioritized on this timeline. The wall moved the curve. The curve has not caught the wall, but the mechanism behind the movement is the policy instrument, and that is the reading the raw figure does not state on its own. Now the second reading, the one that sets the scale of the remaining gap, 700,000 wafers per month. That is Samsung's total dynamic random access memory output, running at the fourth-generation high-bandwidth memory specification as of the current production cycle in 2025. Industry analysts cite that figure widely, treated as analyst level, not audited. But even with the usual margin on estimates of this kind, the ratio is not sensitive to small errors. 60,000 against 700,000 is a ratio of roughly 1 to 11. The challenger's entire stated high-bandwidth memory allocation is less than a tenth of the incumbent's total dynamic random access memory output, and the incumbent's total output includes a generation of product, fourth-generation, high-bandwidth memory, that the challenger has not yet reached. Both of those gaps are running at the same moment, on the same instrument, in the same direction. 700,000, 60,000, 700,000. The node gap compounds the wafer gap in a way the headline ratio does not fully convey. A production count on third-generation high-bandwidth memory measured against a production count on fourth-generation is not one delta. It is two running simultaneously and in the same direction against the challenger. Memory generations move on roughly 2-year cycles. A manufacturer entering volume production at a given generation does not automatically step onto the following generation's development cycle from a standing start on the prior one. It must first recover tooling investment, build yield on the current node, and then restart the full process development sequence. The generational lag is therefore self-reinforcing. The gap between the specifications is not a snapshot, it is a rate. The incumbent is running a process it has already industrialized. The challenger is running a process it has not yet demonstrated at volume. Even if CXMT reaches 60,000 wafers per month exactly on schedule, it ships a product the market is already treating as the prior tier. Volume and generation are separate axes on the instrument, and both run against the entrant at the same moment. The ratio within CXMT's own output adds a third layer the headline figure obscures. 60,000 high-bandwidth memory wafers out of a base approaching 300,000 total dynamic random access memory wafers means the high-bandwidth allocation, even at its stated target, represents well under a quarter of the domestic leader's own production. The bulk of what CXMT ships is standard memory. That is not a sign of ambivalence about the high-bandwidth program. It is the fiscal structure of any challenger that cannot yet price the premium product at the margin the incumbents can. Standard memory generates the revenue that funds the stacked memory expansion. The ratio is a constraint embedded in the business model, and it means that even CXMT's own total output is heavily weighted toward the product tier that does not close the gap with Samsung or SK Hynix in high-performance compute. The mechanism behind the node gap compounds further when the yield curve is considered, and the yield curve is the measurement the funding round cannot purchase. Stacking multiple dynamic random access memory dies with connections running vertically through each die amplifies per-die defect rates in a way that compounds with every layer added. Stack 10 dies and the probability of a clean bond at every connection point falls with each one. Incumbents have run these processes across multiple product generations. Their defect rate per bond has been measured, modeled, and corrected through thousands of production lots at scale. CXMT is on its first commercial high-bandwidth memory node. Consider the physical structure. Stack 10 layers, bond each to the next at a tolerance measured in single-digit micrometers across the full area of each die, and the chance that every bond in the stack clears the defect threshold falls with each layer added. The incumbent has been calibrating that bond across 3 product cycles. Its defect rate per layer reflects accumulated process knowledge that is not transferable through a funding round. CXMT is bonding its first commercial stack. The wafer-start count measures how many stacks you began. It does not measure how many came out functional at the far end of the process. CXMT's yield on third-generation high-bandwidth memory is not publicly disclosed. No independent measurement exists at the time of writing. If the per-wafer functional output is meaningfully below the incumbent's yield on its current product, the effective output gap is wider than the 60,000 to 700,000 ratio shows. The instrument reads wafer starts. It does not read functional units shipped from those starts. Those are different readings, and right now only one of them is available from outside the fab. 3 things the delta could mislead on, stated plainly. First, the 60,000 figure is a commitment, not a production audit. Capital raise targets in memory manufacturing have historically taken longer to reach than the funding timeline implies. The gap between earmarked capacity and running capacity is not measured by the same instrument as the gap between running capacity and product shipped to customers. Until independent wafer-level production data exists, the 60,000 reading is the company's own stated target. That is a different tier of fact than a confirmed output figure, and a single tier of difference in memory manufacturing is not a small distinction. Second, the yield gap is invisible in the ratio. If CXMT's per-wafer high-bandwidth memory stack output is a fraction of the incumbent's, the functional production gap is wider than 11:1. The instrument records wafer starts. The commercially relevant unit is functional stacks shipped. No one outside the fab can currently read the second number, and the first number is what gets cited in funding announcements. Third, capital cannot purchase a mature through-silicon connection defect model. Cleanroom space, wafer handling equipment, and process engineers are all purchasable. The accumulated knowledge embedded in a defect model built across multiple production generations is not. The heat dissipation constraints on dense stacked memory at scale, the fragility of bonded die structures under thermal cycling, and the lithography ceiling imposed by equipment controls all sit outside the funding equation. The $4 billion raise moves the wafer start number. It does not compress the physical learning curve, and the physical learning curve is the variable that most directly determines when the functional output reading catches the wafer start reading. Taken together, the delta from 0 to 60,000 is real, and it is large. The delta from 60,000 to 700,000, compounded by a generational lag on top of it and an unverified yield curve beneath it, is the reading the funding headline does not carry. Now, the interpretations the instrument itself does not state. The first is that the capital raise is the mechanism, not the achievement. $4 billion committed to a wafer target is a planned reading. The instrument records funded intentions and actual output as separate tiers, and right now, CXMT's high-bandwidth memory figure is a commitment figure. The distance between funded to reach and shipping at scale has not closed. When analysts cite the 60,000 number alongside the raise, those two figures belong to different columns of the ledger, and treating them as the same reading inflates the output delta. The second interpretation is that the restriction regime is what made the 60,000 figure legible at all. This is the reading that the raw numbers do not state, but that the sequence of events makes clear. The policy mechanism designed to prevent domestic high-bandwidth memory capacity from growing created the only investment environment in which that capacity could grow this fast. The restriction removed the import option. Removing the import option converted a gap in domestic capability from a commercial problem into a strategic one. Sovereign-linked capital moved towards strategic problems on a timeline that market logic alone would not have produced. The policy produced the investment that produced the wafer count, and the wafer count is now cited as evidence that the policy failed. Both of those readings are simultaneously true. The wall moved the curve, and the curve has not caught the wall. The third interpretation is about what the ratio reveals within CXMT's own production base. 60,000 out of approaching 300,000 means the high bandwidth allocation is the smaller share of the domestic leader's own output. The transition from volume commodity memory to premium stacked memory is not something a challenger can execute at once. The revenue from standard memory funds the stacked memory program, which means the challenger's high bandwidth ramp is structurally paced by the margin it earns on a product tier the incumbents have already moved past. The ratio is a self-limiting mechanism embedded in the competitive structure, and it applies to any new entrant in any capital-intensive process industry. The domestic entrant is not the exception, it is the demonstration of the rule. The measurer's plain reading is this. The restriction regime produced the investment that moved the wafer count from near zero to a 5-figure monthly commitment in roughly 3 years, which is exactly the dynamic the policy was designed to prevent. That is a real and large delta. The same reading shows the count sitting at roughly 1/11 of the incumbent's output, one generation behind the product the incumbent is currently shipping, on a yield curve that has not been independently measured, at a figure that is still a stated target rather than a confirmed production number. Both of those things are simultaneously true, and neither one cancels the other. The instrument does not pick a winner. It records two readings and the distance between them and leaves the ratio on the table. 60,000 wafers aimed at a specification the incumbent has already passed is not a losing position and not a winning one. It is the precise location of the gap, dated, and the gap is what the next reading will move or will not. The question this metric leaves open: by the end of 2027, does CXMT's high bandwidth memory allocation cross 100,000 wafers per month on a node that is current rather than trailing? And does the yield data become independently verifiable at that point? Those are the two numbers to watch for the next dated reading. Volume on a current node, confirmed yield. If you track the count on that, subscribe. This channel takes the next reading when the number moves.